never was. To catch them is my real test. To train them is my cause.
Reduction of 4-tertiary butyl cyclohexanone, CM2191 Experiment 5. Hello students, how's your day been? Hope you're not watching this at 2 AM in the morning. That is a time that you should be sleeping. Now, in this experiment, we will explore the reduction of a ketone using sodium borohydride, which is a mild reducing agent, and then we will use TLC, thin layer chromatography, to monitor the progress of the reaction. Recall TLC? How do you monitor the reaction? Now, this is your starting material, your 4-tertiary cyclobutyl hexanone. What are the possible products from this reaction? These two, and they are diastereoisomers. So in the reaction, we will be using TLC to monitor. Later on, I will show you the video, the link to the video of TLC monitoring. Okay, it was done in 1191, so I hope that you can do some revision on that. Now, sodium borohydride is a reagent commonly used for the reduction of ketones and aldehydes. Other reducing agents such as lithium aluminum hydride, they can react violently with water and alcohol to produce hydrogen gas, while sodium borohydride reactions are commonly ran in methanol or ethanol as a solvent, as sodium borohydride is significantly less basic and the acid-base reaction is much slower. So the mechanism of the reduction for this 4-cyclobutylhexanone is shown right here below. So this is a hydride equivalent. Your BH bond that's partly covalent will give electrons and attack to the partially positively charged carbon of the carbonyl group. Breaking the pi bond, it goes to the oxygen, forming this intermediate with the B still carrying a negative charge. Okay, this negative is not on HR, it's on boron. Okay, because boron comes from group 3, it is supposed to have 3 valence electrons, but right now it forms 4 bonds, so it gains a negative charge. Now when you see 3 arrows means that you have woke up or you have a few steps after that to form a final product, which is the alcohol. Now over here, the stereochemistry is not being shown, but later on you need to show it when you draw out the structure in 3D manner. What is the byproduct here? It is boric acid, the acid of boron. Take note that it doesn't mean that when you see a chemical formula with OH, it must be an hydroxide. You can be easily deceived. You see, we have a shenanigan here. Oh, BOH3, so B3 plus and 3OH minus. This is not the way to do it. Boric acid, when you draw it out, it looks something like that. BOH. Okay. Trigonal planar, bond angle 120 here. It is a polar molecule. Dissolves very well in water. When it dissociates, it will form H plus and the conjugate base O minus over here. Okay, so this is boric acid, and recall that boron is a metalloid. It is not a metal, so it will not form the alkaline. Now this tertiary butyl cyclohexanone has 2 conformations. One where the tertiary butyl group is equatorial, and the other when it is axial. So for most substituted cyclohexane ring, it will rapidly interconvert between the 2 conformations, so at any time the solution would be a mixture of both conformers. When the substituents is small, like in the case of deuterium, okay, this very small atom, period 1 with only a 1s orbital, the 2 conformers are almost equal in energy, so it is practically a 50-50% mixtures of the axial and equatorial conformers. The bigger the substituent, however, the higher energy the axial conformer becomes, and therefore the ratio of the equatorial to the axial conformers increased. And when the substituent is a third butyl group, now T butyl group, It is a locking group, very big. The axial conformer has severe steric interactions that make it very high energy and therefore very unfavorable. In the case of third butyl cyclohexanone, the axial conformation is practically not observed, and the cyclohexane ring is locked into a single conformation with the tertiary butyl group equatorial. You can see from the photo here, or the picture here, it will never adopt the axial third butyl group. Too much strain there. Analogously, the 4-third butyl cyclohexanone is locked in the conformation with the third butyl group equatorial, and thus the two faces of the carbonyl groups becomes non-equivalent. This means that when the hydride source, sodium borohydride in this experiment, attacks the ketone, it will result in the formation of two different stereoisomers of products, depending on which phase of the carbonyl it attacks. Furthermore, because the two ketone phases are non-equivalent, one can expect to see the stereoselectivity in the reduction, meaning that one diastereomer will be more prevalent than the other. Which diastereomers do you think will be the major product? And why is that so? Alright, so as shown in the diagram here, this is a hydride equivalent. That's why we use a prosophy before and after. It's not really a hydride, but hydride equivalent. We call it a HB covalent bond. Okay, so over here, the first picture shows that the hydride is being delivered from underneath. The right word to use is, it is a antafacial attack. Okay, I know some of you like to just say that, okay, it's a plane, so you can attack from the top, TOP. Okay, that's a Korean singer, very popular now, or the bottom. But these are not the right word to use. So use antafacial if it comes from the base and from the above. The actual word is suprafacial. Okay, oops. Suprafacial. Okay, supra. Yep, suprafacial, not superficial. Suprafacial. Superficial is not good. So it delivers the proton from the equatorial position and hit the CO double bond down, and hence you get an equatorial hydroxy group. Now we can ask ourselves, why would there be two possible reactions? In any organic chemical reactions, we can always look at the mechanism, and we need to look at the TS. What is TS? TS, transition state. Take note, this is not an intermediate, it's different. A transition state cannot be isolated, and there are no real bonds present. It is just a hypothesized molecular structure that bond forming and bond breaking is taking place. Whereas an intermediate, you can isolate it and there are real bonds being there. For instance, carboxyl ion, a third butyl carboxyl ion, quite stable indeed. So these are the transition states you can draw out. We call this the felkin-anh model. If you learn organic chemistry, you have to know this model. Felkin-anh model talks about which trajectory of the nucleophile is going to attack the sp2 hybridized carbonyl carbon. Here in the 4-third butyl cyclohexanone, we have a CO double bond. Trigonoplanar, and the borohydride can come in from two ways. First, from this angle, the equatorial delivery, or on the right, the axial delivery. Now see that this Newman projections, right, shows two different environments of how the hydride equivalent is going to come in. Suprafacial attack will cause this to interact with both HA and HB. So imagine this is the structure of your 4 tertiary butyl cyclohexanone. You see that if the hydride equivalent is going to come in from this trajectory, okay, it's going to hit these axial atoms, even though they are hydrogen. There's some kind of interactions here at the borohydride angle. So at this angle, borohydride, not the burger, borohydride, if the U inside there's a German alphabet, borohydride angle, about 107 degrees. Okay, it will attack. On the other hand, it can come in from antarafacial manner and deliver your hydride. So we can analyze this mechanism using the what diagram? What structure do we call this? Sawhorse. Sawhorse structure. We can see the 3D manner in which all the bonds are staggered, pointing up or down. So take note, it's sawhorse, not seahorse, not seesaw. Sawhorse. So if you bring your borohydride undergoing an equatorial attack, come in, break the pi bond, push it down. This is the transition state. How do you know this is the transition state? You put a square bracket around it with a dagger. A dagger. Not positive. It doesn't mean two positive charge. A dagger. I know this doesn't look like a dagger. Okay, but take it like a dagger. Okay, so this is a transition state where you have bond forming. You see bond breaking, dotted line, bond forming. And the second step, hydride attack, and finally gets protonated. You get the hydroxy group. Okay, I hope you can relate these two transition state diagram from different angle. This is your what structure? Your Newman projection. Newman, not old man, Newman. Newman, and that is sawhorse. Relate these two. You have to be good in drawing these structures in your exams. Conversely, we see this axial attack where you bring your hydride equivalents from the vertical manner. Okay, and then the same thing goes in another view, transition state. And you woke up and you get the equatorial hydroxy group. So after the synthesis, we will use both the infrared and the NMR spectroscopy to analyze the products. Now these are the literature IR spectra. So you can compare yours to the ones below to determine how successful your reactions were and that you have indeed made the correct compounds. Now before you take a look at all this, right, just see a big picture. Which one belongs to your starting material? The 4-3-butyl cyclohexanone. Which one is it? One distinct feature is what? You look at the region for IR, right, where you want to differentiate something that has a carbonyl group and the other molecule that does not. First thing you look out for is a CO bond stretch. It is very significant and prominent to you, lying between 1650 to 1800, a sharp and strong peak, both sharp and strong. Okay, so as I've circled here, this must be your ketone. Okay, and see this is absent, so there's no CO double bond here. Another clue you can look at is the chemical formula C10H18O against C10H20O. Of course, the one that undergoes a reduction, would have gained the hydrogen atoms. And you can also see from a name, it's cyclohexanone with ONE against hexanol with the OL. You can also see that the spectrum on the left, between 3200 to 3400 wave number, there's this absence of a huge broad peak. So you see this part's missing, whereas for the other spectrum you see that this is rather broad. It's indicative of hydrogen bonding that exists when you have the OH group. And of course this must refer to the alcohol, not the ketone. Okay, so this part's missing. So next you can use the NMR to monitor the success of your experiment. As mentioned just now, you could get two products out of these procedures. And how do you measure what is the percentage yield of each of the conformers? So we can analyze using the area underneath the signal in the NMR spectrum. Now you see two small signals at about 3.5 parts per million and the chemical shift 4.03. The one that's at 4.03 ppm would refer to the axial hydroxy group, 3.5 ppm equatorial hydroxy group. So the percentage of the cis isomer of the alcohol being produced is just a very simple equation. You take the area of the 4.03 ppm signal over the summation of the area of the 4.03 and 3.5 parts per million signal, and then you multiply by 100%, you get your percentage yield of the cis isomer. Now let's analyze why this is the case. You see that right here we are having the equatorial hydroxy group. So if you look from another view, you see that it can couple with HF, HE, these two protons, and HB and HC. Okay, we are looking at the coupling between HA and HE and HF. Why don't we look at HB and HC? Because they're too far away. So normally most of the time what we do is we take a 2J coupling, if not 3J coupling, 4J, or maximum 5J, because it gets increasingly weaker for the coupling constant as the bonds are further away. So these numbers, the superscript represents the bond distance. So for instance, if you look at HA-HE coupling, it is a 1, 2, 3. A 3J coupling, so we can put A and E. What about A and F? A and F is also 3J coupling. So it's 3J coupling for AE, and AF also 3J. What about AB? 1, 2, 3, 4, 5. 5J. So that's why we don't really consider in the NMR spectrum. So the first thing we look at is the one with the highest frequency for the coupling constant. That is your two anti-paraplanar protons, HF and HA. So they experience the greatest spin interaction, and you see that it is 10 Hz. So the first splitting causes it to be a doublet because you take a n+1 rule. So 1 plus 1 is 2, so it's a doublet. And after that, you split it again with the other HF, so another doublet. But because they have the same coupling constant, so they overlap. So you get a 1:2:1 ratio, which is a triplet from the 2 HF. Next, you use HAN coupled with HE. Again, HE are both identical, but their coupling constant right now is not so great compared to HF because it is at an angle, not 180 degrees. You can look up at the Laplace equation to learn more. Laplace equation on NMR. Okay, you can do some research on that. So each of those signals gets split again into a triplet because 2 plus 1 rule says triplet. So all in all, you would have triplet of triplets. Okay, triplet of triplets. Now for the other isomer, now you have the hydroxy group pointing axial position, and that means the HA will be in the equatorial position. So now we do an analysis again. Okay. HA will couple with HE. HA will couple with HE and cause it to form a triplet. So you see, HE, you get a triplet. It will also couple with HF. So you see the first part when it couples, you get a triplet 1, 2, and 3 due to the two identical HF. But if you look carefully, HA and HF is at the same angle as HA and HE. If you look from that direction, you see that they have the same coupling constant. That's why when this signal couples with He again, it splits to another triplet, and they all overlap. So in the end, you will get a pentat instead. 1, 2, 3, 4, 5. That's the signal you will get. Okay, so here comes the reaction setup. Dissolve 0.5 grams of the 4-butyl cyclohexanone in 5 ml of the 95% ethanol. So you'll be using a 25 ml round bottom flask because of the total volume of the solution. It is not as high as 25 ml. So you're going to stir properly, make sure all of it dissolve, no solid remaining, and then slowly transfer 0.4 grams of NaBH4 into the solution. Now the mixture will become warm because it is exothermic, and you need to cool it down in a cold water bath. Take note, this is cold water bath, not ice water bath. There is a difference between cold and ice. Okay, ice is cold, but cold meaning that possibly 15 to 20 degrees Celsius. This is cold, but ice is 0 degrees Celsius. Alright, try to keep the temperature of the reaction mixture between 25 and 35 degrees Celsius. Now at the same time, you have to monitor the reaction when it will finish. It doesn't mean that when the lab manual says it should finish under an hour, then you just stop at an hour. In all chemical reactions, especially in organic chemistry, you have to check intermittently whether your reaction mixtures have finished reacting or it is still in its infancy. Okay, you can't just leave it to boil overnight for 24 hours thinking that okay, it will be perfectly fine the next day I come back from home. But your compound may go chow tar, okay, it may be charred, and you may have to start from step 1 again. So monitor the reactions using TLC, thin layer chromatography. You can find the video at this website listed here. You can go on it. But here I will give some preview. Okay, use of stain and hot plate. So this is not a typical TLC that you performed it last year in 1191. So here, what are the stains we are using? We'll be using a stain that's prepared beforehand. N9-aldehyde. What is the formula? What is the formula of this? Here we go. Benzene ring. Okay, benzene ring, like the formula suggests, it is an aldehyde. So this is your carbonyl carbon, aldehyde, and methoxy group. Okay, N9-aldehyde. Now this stain was prepared for you by the lab officers, so thank them for it when you go to the lab. They had to use absolute ethanol. Read the lab manual, it says absolute ethanol. What's that? Absolute ethanol? Yes, that's right. Your absolute vodka. The one that some of you may consume during party, New Year celebrations. They also had to add corn sulfuric acid, told you before, battery acid, and glacial. Glacial. Acetic acid. Wow, big word. Glacial. What does glacial mean here? Glacial acetic acid just means that it is water free. It's very dry. Totally no moisture. Okay, glacial. Sounds like the acetic acid is so graceful and elegant. Glacial acetic acid. Anyway, you don't have to worry about the preparations, and this look purple to you. So what you do is, right, you dip your TLC plate inside the N9-aldehyde after putting the spots. Okay, so this is your TLC plate. Draw a line using pencil, sample, reaction mixture spot, cold spot, and your starting material. So once you spot it, run it up first. Okay, of course you're going to stop at some point. take it out, dip into the stain. So the whole part should be soaked in purple color or maybe light purple color, and immediately you should already have this in place, the hot plate that's hot. Not too hot, okay, just hot. And you place this hot plate above. So the side with the sample, please make sure that it faces the top, yeah? Don't let your sample face down the plate, it will disappear, it will all be burned. Okay, and monitor the TLC plate as it changes color. You can't just stop here and go out for a break, lunch break or toilet break, come back, you see it's all black. There was a case, I think it was spark was seen for some of the students who did this. So for the workup, now once the reaction is complete, quench the reaction mixture by adding the water. DI water is fine. You can use tap water, but we provide you with deionized water, so use that. Then we add an ml of 3 molar HCl. Drop wise with caution. Why? H2 could be produced because you had used excess of the hydride, borohydride. In the presence of a protic solvent like water, a very good protic solvent, you would have the generation of hydrogen gas. Very flammable indeed, but it's a very clean and green fuel. So about 10 minutes, you see, about. You should make your own description, okay? When the evolution of hydrogen gas becomes slow or ceases, heat the mixture to boiling. Again, do not just turn the knob and spam it, okay, to the highest temperature and start to boil. You may not be able to control it afterwards. Allow the mixture to cool down to RTP afterwards, and you get a white inorganic solid. But that's not what we want, okay? Discard it before the extraction, not after. So you do a filtration first and continue with the extraction. Now strike the reaction mixture with diethyl ether, organic solvent. This can be a bit pungent, so try not to spill anything and do it inside your fume hood. Very pungent. Okay, you stain your shirts, so please wear your lab coat nicely. Wash the combined ether layers with water and dry the combined ether layers with anhydrous sodium sulfate, drying agents here. And finally, use the rotovap to remove the solvent. Now this part, do not leave it there for very long. Like I said earlier on, put your sample inside, rotate for a while, monitor. If you see that volume is decreasing, good. And after a while you see that you think it's totally dry, there's no more solvent, okay, stop heating, take it out. Because if not, your ether will just be refluxing, so-called refluxing inside the rotovap, evaporating, cooling, evaporating. It's not gonna work. Give some chance to your friends, don't just hog. Stop hogging at the rotary evaporator. And then finally, just weigh your products and then submit in a sealed plastic bag for us to grade it. And remember to answer the question in the lab manual. Thank you, have a good day. See you.